Hello, good morning, and welcome to the monthly webinar for Spotlight Talk of Journal of Computing Information Science Engineering, JCISE. Today, it's our pleasure to have Professor Mian Li from Shanghai Jiao Tong University to give a talk of his latest paper. Professor Li is one expert in design optimization, and today we're going to hear his latest work entitled "The Data-Driven Sensor Selection for Signal Estimation of Vertical Wheel Forces in Vehicles." Mian, please go ahead.
Okay, thank you very much, Dr. Wang, for your kind introduction, and good morning, everyone. This is Mian Li from Shanghai Jiao Tong University. Good to see you here. The topic of my today's presentation is data-driven sensor selection for signal estimation used on the vehicle to estimate vertical wheel forces. I'd like to acknowledge my co-authors here. So today's talk including three major components. First, I would like to introduce the major background on this data-driven modeling. And second, we will briefly talk about the data-driven load estimation in vehicles, which is first part of this work. And then the major part of today's presentation is to discuss this data-driven sensor selection. And this whole seminar will take about 35 minutes around, something like that. So let's talk about data-driven modeling first. In control engineering, we all know that the modeling of dynamic systems is a very, very popular, but also very, very important work, because when we, no matter try to design a new controller, or we try to predict the performance of the system, as well as when we trying to conduct a simulation, for example, like digital twin, or conduct the health monitoring system, we all need to model the dynamic systems. And it's very, very popular in this area. And so this is something that we have to conduct at the beginning. To conduct the modeling of dynamic systems, usually there are two ways. The first one is called first principle modeling. Usually, when we do this, we will use the law of physics, like Newton, like others. Basically, this type of modeling will be used to model the system with a relatively simple structure. More and more, because of the system become more complicated recently, so people developed many, many different types of data-driven modeling techniques, which can be classified into two types, like a gray box or a black box. The major difference between gray and the black is whether we have a clear model structure and do we have any physical meaning between the input or the system output. So basically, the major idea here is that we know the input U and we know the output Y. We need to figure out what is the system in this case, this block in the middle. If this is the black box, then sometimes we know, like a neural network, we know the input, we know the output, but we don't know why or what happened in the system inside. So this is a typical data-driven model structure or a method people use, a type of method people use for dynamic systems. Very related topic or term called system identification, which is very close research area, which is talk about the data-driven modeling. And in this system identification problems, usually this is a process we try to develop or improve a mathematical representation of a physical system, but using experimental data, not just simulation data. So in this case, the system identification method will help us to develop a more accurate or more accurate or efficient system modeling using experimental work. So this is something that we also need to use later in our work. Another important terminology we are going to discuss today is called the sensor-to-sensor identification. It is a very special type of system identification, but not the same. For sensor-to-sensor identification problem, the biggest difference is that in this case, the input of the system U here is typically unknown and non-stationary. For our case that will be discussed today, the typical example is that the vibration transmitted to the tire from the road surface to the tire of the vehicle, for example, because we don't know what will be exactly that input from the road. So sometimes this U we consider is unknown. So in this case, for sensor-to-sensor relationship, G, this relationship is trying to describe the relation between two types of outputs, Y and Z. And in this case, what we are interested in is, do we have or could we build a relationship, build a modeling to describe output Z using the output Y, because U here is unknown. So for this type of work, we call it sensor-to-sensor identification. And this type, if we look at this system configuration compared to what we discussed for the system identification, actually, sensor-to-sensor identification problem is not a very typical system identification problem. So in this case, they are not very similar. Today, what we are going to discuss majorly will be sensor-to-sensor identification problem. To continue specifying the sensor-to-sensor modeling, in this work, we focus on the linear time invariant LTI systems. Basically, it means that we would like to use the non-causal finite impulse response model, like we show it here, to represent the system output Z. The input will be Y, the output will be Z. EK here is the residue. And we notice this is a linear function of Y, and summation of that will give us the key ZK value. In this formulation, we have the linear time invariant function. Model parameters can be obtained with the experimental data using the state-of-the-art system identification techniques. The reason we would like to use the FLR models because they are very simple. You can see the structure, the system structure is very, very straightforward. And another beauty of using this structure is we do have bounded input and bounded output stability, which is very important when we talk about dynamic system. In this case, we know what will be happened. Basically, we know what will be the boundary of the worst case. The sensor-to-sensor model in LTI system actually has been used previously or originally from the structured health monitoring of advanced aircraft. It has been used by NASA, proposed by NASA previously, and now we use it not in airplane, but instead in vehicles. However, we know that for vehicles, a typical problem is that vehicles are not linear. They are typical non-linear systems. And for this linear time invariant LTI system, this method will not be directly applicable to nonlinear systems because we have to deal with the nonlinearity happen in the system. And the key idea is how to do that. So this is the background that we will use in the later discussion today. The second part we would like to discuss is the load estimation in vehicles. We know that when a new type of cars are made, there are several major procedures like a conceptual design, engineering design, and we also need to build some prototypes to conduct the design validation work. And if everything okay, everything going well, then we will do the manufacturing and launch the new vehicles to the market. So the design validation is a very, very key step during the vehicle development. For design validation for vehicles, usually what people do is they will instrument many different type of sensors on the vehicle prototypes, and let those vehicle prototypes running on different type of field test. Here we show 4 major different type of sensors we consider or used in our work. For example, the force transducers, displacement sensor, accelerometer, as well as string gauges. So when prototype are developed, they will be equipped with those sensors, and those vehicles will run on different type of test roads to mimic the real driving situation. So during this procedure, the data will be collected as, for example, the sensor data will be collected and analyzed for different type of road conditions. So we all know those, when we look at those prototypes running on the field test, we know that there are large number of sensors are deployed in the prototypes. However, this type of work will lead to several drawbacks, unfortunately, but it's still the current situation. First, the high cost. Usually, for example, like this central, the wheel sensor, the wheel force sensor shown on the left page, the left figure. The price of the sensor is very, very expensive. It's not a piece of cake. And to install and use those sensors is also a very time-consuming and difficult job. And we also need to spend a lot of time to conduct the maintenance to make sure those sensors can work. So usually for automobile manufacturers to use those sensors as well as maintain them is not a piece of cake. It's always a difficult job, which is also the reason that to develop a new type of vehicle, there will be a lot of time spent on this road test. So it is very appealing to obtain signals, sensor signals of interest without directly measuring them. That's lead to this new terminology, or people call it soft sensor. The paradigm of this soft sensor actually is not very difficult to understand. Soft sensors basically is trying to use some easy to measure variables or sensor data, which be available on the vehicle, with some mathematical models to deliver the estimation of those so-called hard to measure variables, like we showed here in the middle of the figure, in the middle of the page. So the soft sensors basically including some easy to measure variables or sensor data, and also some mathematical model. Those mathematical model should not be very complicated to build or run, because remember those sensor or those soft sensor need to be also running online with the vehicle together. So most of the time it cannot be a very, very huge or large computational heavy models. It has to be light. Here we define this hard to measure variables are those sensor data or those sensors which will be only measured in a short period of time. For example, during some offline modeling stage, we will use those sensors to get those hard to measure data. But during the online estimation stage, for example, after we obtained some training data, then we will use those data to, as well as the model, to replace these hard to measure variables. So For this work, actually, we published a previous paper to discuss this work. Also in the same journal, actually, we published the two papers in a very close period of time. To be specific for the soft sensors for estimation wheel-center forces, here is our paradigm. The easy to measure variables, including, for example, the displacement sensor, accelerometers, and we build a sensor-to-sensor model in this work and trying to estimate the wheel-center forces. The cheap sensors, usually, the reason we choose them because they are compared to expensive sensors, they are really cheap, like tens of dollars or something. But the expensive sensors are really compared to them, like thousand or even, sorry, the tens of thousands of dollars for these wheel-center forces. So in this case, the main idea is that we're trying to use the easy to measure variables like the displacement, acceleration, those data to estimate the wheel-center forces through the sensor-to-sensor modeling. So this is the main idea that we are going to use in this work. So can we obtain this sensor-to-sensor model? The question is, answer is obviously yes, we can do that. So obviously, first thing came to our mind is, could we use a first principle model like the laws of physics, right? However, due to the complexity of the vehicles, it's really hard to build, to obtain high accuracy first principle model for the full vehicles. So unfortunately, we have to go to the data-driven models. And in this case, we now use the sensor-to-sensor identification problem that we mentioned in the background discussion. In this case, the paradigm is we classified the output of the system into two categories, Y and Z. Basically, those Ys are easy to obtain, so we try to use them based on the relationship from Y to Z. We try to see whether we can obtain the Z value. How to identify the nonlinear relation of G, because this is a vehicle, right? It's not a linear function. So sorry, this is not a linear system. So we have to figure out how to identify the nonlinear relationship through some set of linear models. So the idea here is trying to approximate a regional system by a linear time invariant system under each work condition. So basically, we believe that under each work condition, the system can be approximated by a linear time invariant system, so that we decompose, actually, in another word, decompose the nonlinear reality into different working conditions. Excuse me. If we can do that, then what we can do is we can identify model family G from G1 to Gm using FR model structure under offline or known working conditions. If we know that the capital M working conditions are there, then for each one of them, we can build a linear function model to represent that system. Then question becomes another one. Can we determine which unknown working conditions this vehicle is running on during the test or public roads? Because when we drive on those roads, or the driver or the system will not tell you, hey guys, we are running on a high-speed way, or we are running on the block Belgium road. No, that's not the case. So here, the key question is that we have to identify the road condition automatically so that we can apply this nonlinearity capital G family. So here is the schedule, we call the scheduling method. First, we decompose the easy to measure variables again into two groups. In this case, Y will be divided into W1, W2, two subsets. Now, we can try to use the similar sensor-to-sensor identification method to identify the relationship from W1 to W2. But knowing here that both true values of W1 and W2 are known, then in that case, if we know the estimation is very close to the true value, then we have a good system identification, or we identify the correct working condition. So in this case, what we do is that we, in addition to the original sensor-to-sensor modeling G, we generate a new model family called H, and we call this family auxiliary model family H. And the reason we like to build this one is trying to use this family H as a classifier based on system identification, and we can classify using the figure on top right to identify what is the most accurate working condition the vehicle currently is running. And we put this classifier into the framework. So now with this offline build model H, we can use them to identify, based on the known input and output between H, then we can identify the working condition. And the working condition will be used to tell us or to select the appropriate family in capital G. Now we can use this whole framework to conduct our work. And this work also has been published in the journal. Now, we also conduct the experimental validation using the true vehicle, and also as using a sketch of the suspension system together. The demo has been conducted with 5 known working conditions, and we are trying to use them to identify 3 unknown working conditions. And the model scheduling process actually is trying to still identify the vertical real force and its estimation. And the bottom one on the in the figure on the right demonstrate the evolutionary of the model, which means the change of the models. So the estimates of the proposed methods are close to the measurements you can see from the figure. And when the driving condition has been changed, and the model can easily identify the most appropriate working condition to select the model and to conduct the online estimation. In addition to the this 5 working known conditions, we conduct 35 online working conditions validation, including random and periodical road profiles, braking and curve running. We use the environmental fit to identify the relation, how good our estimation is. And the proposed estimator outcome, it turns out that the proposed method outperforms typical linear and even nonlinear estimators, as we show in the table on the right. So we show here the mean and the variance of the fit value. The ideal fit, the last one, is because we know the working condition. We can estimate that when we conduct our lab work, when we in our lab, we can do that afterwards. So the ideal fit basically is the best case for the ideal case, basically, which cannot be even better than that. So if you look at that, we notice the mean value is very close to that, and the standard deviation is just a little bit worse. So the scheduled estimator is the method that we proposed. Excuse me. We also actually not just conducted the lab experiment. This work actually has been applied in the real industry. We have installed this system on multiple vehicles, test vehicles, and has been used not just in China, but also in some other places to conduct this real force estimation work. And in order to do that in a very smooth way, we also conducted this edge computing solution. And this is another paper we published, similar related paper published in CET. If you are interested, you can refer to that work. We also another question we missed is that during the sensor, sensor-to-sensor identification problem, sometime the sensor will corrupted or the data will be missed. And in that case, it is very vital to detect the potential abnormal situations or failures of the sensor as early as possible. So we also developed the data-driven sensor fault detection algorithm, and this related paper also published recently in RESS, which is reliability, very top journal in reliability, I guess. So to summarize this work, the second part work. So we built a linear model with a very simple structure, and this gave us a lot of benefits. For example, low computational cost as well as memory request. As we mentioned, that we installed edge computing device on the vehicle, which can quickly interpret the data without going to do the clouding calculation for neural network type of calculations. And this model has a very simple model training and turning procedure. And compared to other methods, we have a very short training time and small training data required. The major contribution of this part is compared to previous work, the proposed soft sensor is very simple, effective, and reliable. Okay. Now, the problem is that we are not very clear for the manner of selecting the easy to measure variables. As we mentioned, we just use them. We don't know which one we should select or which one we should not. So next part, we talk about the data-driven sensor selection. The motivation of continuing this work is trying to identify what are the K most cheap sensors out of S of them that are most related to the expensive sensor. Basically, in our current setup, actually, we have 34 different types of candidates that can be used, can be selected to predict expensive sensors. But question is, do we need to that many sensors? 34? We don't know. So we need to decide whether we can reduce this number. We can choose the, for example, K out of S, say how they work. So difficulty here is that how to choose K, or what are the combination of K different sensors from S, total type of sensors or total sensors. There are many possible choices, and is impractical to enumerate basically. And secondly, there is no first principle model. So the question is, can we still do that? The objective, we want to develop a fast sensor selection method that can effectively determine K most related cheap sensors for this work. Back to the sensor-to-sensor LTI model, we have, if we put them into the matrix formulation, we have the this formulation here. This is just the metric representation of the previous formulation, nothing special. But here, we just specify the residue follow the normal distribution. And another thing we learned from the literature is there is a term called margin distribution. Under the Bayesian assumption that we have this theta 1 to theta s all follow the normal distribution, then it can be verified that z must also follow normal distribution with this formulation, and the theta must be larger than 0. So in this case, what we can do is directly we can apply the likelihood function. We call it marginal likelihood function, and we can try to maximize this function with respect to theta and epsilon. So in this case, the optimization can be done with respect to those two variables. If we put the selection question into the picture, like select the k out of s, definitely k should be less than s, then in this case, we can use additional variables like a cs to encode whether the s easy to measure variable is selected or not, and formulate this optimization problem. And nothing other than this C1 to CS encoding, actually the second formulation is the same as very similar to the first one. Okay, then to solve those, to solve this second formulation actually is not that easy, right? Because we have 0, 1 variables. So there are two things we conducted trying to make this optimization solving more easier. First, we conduct a relaxation from 0, 1 variables to with convex constraints between 0 and 1. So we replace these non-convex constraints with convex constraints. And the second step is we applied this inequality using the inequality log that s less than trace x minus I matrix, because this is true for any positive definite matrix x. So in that case, after this transformation, we can change the original optimization problem into this convex optimization problem. And in this case, the key chip sensors are selected by sorting H1 to HS in a descending order. So we also try to analyze the computational cost of this problem, and unfortunately, to do the inverting XS is problematic because the data size n could be really, really large, because we here the data we looking is the trial test data on the vehicle. So the number of n could be really large. And secondly, the XS is close to being singular sometime. If that is the case, then the system will become really unreliable. So what we do is we conduct this QR factorization in advance, and we conduct this one before we really solve the optimization. The benefit is that this will make the system numerically reliable and far more efficient when n larger than Sn here. Due to the time limitation, I will not go through every details of this calculation procedure. Everyone who are interested can refer to the paper for the details. But with this three consideration, we can easily solve this problem. And we also compared this method with the group lasso method. Group lasso method has been considered as a commonly used sensor selection method in the literature. So here, we conducted analysis with different data sets n here, n from 1000 until 2000, and the proposed method, the fit, the higher the better, obviously, outperform group lasso for most of the cases. And we also consider the system has different orders. For example, FIR models, we can have different FIR models, different order of FIR models, like n from 30 to until n to 60. Of course, the higher model, the little bit more complex of the model itself, but there will be also more parameters to select. And even with that, we notice that compared to group lasso, that our method also have better fit value. So in this case, we try to demonstrate the proposed method has a higher fit and is more reliable than the group lasso at least. Also, in terms of computational method, what we conducted, the analysis is trying to compare to the, for example, the computational time, the running time with the numeration. Excuse me. When we can look at those two figures shown here, when we have a case larger than 3, which are typical situation compared to s equal to 15, for example, the fitting performance of the proposed method is very close to the enumeration-based method. And we notice that in that case, the enumeration method definitely is the the golden rule here, because we numerically selected the best. However, the running time, we can see that when we have a larger k, larger than 3, then the computational time of the enumeration method will be highly increased compared to the proposed method. The computational method for the proposed method will not change a lot due to the change of the k. So to summarize, the major characteristic of the proposed method is we think it is very efficient, effective, and easy to implement during our vertical wheel forces estimation work, and it is applicable. It is really applicable to estimate other loads in vehicles, and we also demonstrate that later in our later work. Other than the vertical force, we can also use that to estimate other key performance of the vehicles. The major contribution of the proposed method compared to other sensor selection method, the proposed method has some advantages. For example, it only requires smaller possible subsets of the easy to measure variables while retaining the same model accuracy. Definitely, we can use a smaller subset of the easy to measure variables to conduct the similar work. And during this optimization work, actually, we don't need to tune hyperparameters using cross validation or additional data sets. Basically, we use pure optimization technique to solve the problem. So there is no tuning procedure required. And if we do have additional constraints, for example, if there are some budget constraints or other constraints people would like to apply in this work in the future, then we can easily considering those additional requests. So this method is more flexible in our opinion. So there are some also future works that we have been considering to continue this to continue our work. For example, we can try to obtain the theoretical gap between the global optimum and the relaxed solution of the sensor selection problem that we proposed. Currently, we haven't conducted this theoretical analysis, And of course, we can extend this case of LTI system to the one of the so-called switched linear system, which is more realistic but complex than the LTI system, which may be an interesting direction for us to go in the future. Okay, finally, in this presentation, I would like to acknowledge the sponsor of this series paper and research work, including Shanghai Automotive Industry Corporation, Weimar, China, as well as the National Nature Science Foundation of China. I believe this is all my talk today. Thank you very much for this, for inviting me here. And next, I would like to answer any possible questions. Professor